And we're back. So in the last section, we did inverse trig functions and did integration for inverse trig functions. So it would really help us if on the bottom of these fractions, if we have expressions with x, we could get them into something with x squared plus or minus some other number squared. And that's where completing the square comes in. So we're going to work on completing the square, then we're going to take a look at some areas that are bounded and do definite integrals, and then we're going to put it all together and do integration techniques. So this will be the end of our integral rules. Actually, last one was the end of new integral rules. All right, so completing the square, we want to write polynomials as the sum or difference of two perfect squares. So like u squared plus b squared, or u squared minus b squared. So it's just a three-step process, and I know it looks kind of cumbersome, but it's not really all that difficult. So the first thing we do is if there's a number on this x squared in the front, we factor out that number. So factor out a is really what's happening here. Next, we take whatever's in front of x with the sign, and we divide it by 2. And then we square it. So we find b over 2, we square it, then add and subtract it. Seems weird, right? But we were going to add it, and then we subtract it. All right? So when we add it, that makes this guy right here, the first part, that now becomes a perfect square. It becomes that. All right? And it is whatever sign that is there. If b is negative, then this would be a minus. All right? And then this guy over here, if we take the square root of that and square it, that's also a perfect square. So that gives us something squared plus something else squared. All right, so it gives us the sum of two squares, which is what we want. Or u squared plus something else squared. And we've already kind of used b, so I don't really want to use b again. How about d squared? All right, so now let's try that here. So we got x squared minus 4x plus 7. We can't really do any sort of substitution here. So let's try and complete the square. So here's my b right here, negative 4. Divide it by 2, we get negative 2. And square it gives us 4. So if we write this now as x squared minus 4x plus 4 plus 7 minus 4 down there. So now we've added 4 and we've subtracted 4. So technically we haven't changed the bottom here. If we put these guys together, this factors perfectly into x minus 2 squared. It will always just be whatever number we had in here, right there. Plus, and 7 minus 4 gives us 3. So we could say this is the square root of 3 squared. All right, so now this becomes my u, and then my du is just dx. We've already got that. And we've got something squared plus something else squared. That means this is our tangent. So this would be 1 over a. So my a here is the square root of 3. So 1 over the square root of 3, arctan of u, which is x minus 2, over a, which is the square root of 3, plus c. There's my answer. All right, so that's a neat little trick to get things into nice arctan forms. All right, we'll just practice some completing the square down here, and then we'll go on to the next one. So again, if we have a number here, we factor it out. So we're going to divide everybody here by 2, and we're going to write the 2 out front. So we get 2 times x squared minus 4x, same thing as that one, plus 5. All right, so now we take this guy, we divide it by 2, which gives us negative 2. We square it, which gives us 4. So this would be 2 times x squared minus 4x plus 4 plus 5 minus 4. So this would be 2 times x minus 2 quantity squared. I guess we'll leave the 2 all the way out front, plus 1, which is also a perfect square like that. And now it's perfect square, adding them together. All right, last one here. Let's go over here with it. And let's rewrite it as negative x squared plus 3x, and it's plus nothing. We're going to factor out the negative, and we're left with x squared minus 3x. So now we're going to take this negative 3 and divide it by 2, and then square it. Well, that's going to be negative 3 over 2 squared is 9/4. So what we're going to get, and then this is inside the parentheses, is x squared minus 3x plus 9/4 minus 9/4, like that. All right, so now we've got the negative outside. This is going to be exactly x minus 3/2 quantity squared. And this is minus 3/2 quantity squared, like that. There's our perfect square. All right. It's not always pretty, but it is always we can always do the perfect squaring thing. All right, and there it is right inside of there. Oh, it's coming back. Find the area of the region bounded by the graph of f of x equals that, the x-axis, and the lines x equals 3/2 and x equals 9/4. So here's what that looks like. Here's x equals 3/2. Here's x equals 9/4. Here's the graph there. Here's the x-axis. So this little pink section is the area that we are trying to find. So the way we'd write that as an integral, it'd be the integral of 3/2 to 9/4 of just this function, 1 over the square root of 3x minus x squared dx. All right, now this should look familiar. It's exactly this guy here, 3x minus x squared. All right, so it actually equals all that. All right, so now this would equal the integral from 3/2 to 9/4 of, I'll just put dx on the top, dx over the square root negative x minus 3/2 squared, and was it minus or plus? Minus. Minus 3/2 quantity squared, like that. So now this doesn't quite match, but we've got a negative outside. Let's go ahead and just distribute that negative. So it'll give us the integral from 3/2 to 9/4, that's not changing. Dx on top, still not changing. The square root, if we distribute the negative, this one will be minus, and it will change that one to plus. So we can just write that one first. 3/2 squared minus x minus 3/2 squared. All right, so we've got a squared minus u squared. Do you remember which one that was? Well, do you? All right, a squared minus u squared, I believe, was sine, right? We can go back and look if we don't remember. If we're not sure, we always just go back and look. It's back here as always. A squared minus u squared, arc sine. There it is. Yeah, all that stuff's still here. All right, so this should be arc sine. So this is one, let's see, there's no 1 over a for arc sine. We don't have a du, dx. We don't have to put another factor in there. So this is just the arc sine of x minus 3/2 over my a, which is also 3/2. Strange how that worked out. And this is evaluated from 3/2 to 9/4. All right, so now we're just going to plug in. We get the arc sine of 9/4 minus 3/2 over 3/2 minus the arc sine of 3/2 minus 3/2 over 3/2. All right, now on the AP exam, if you want to, you can stop here, but this one's not so bad. So this is 0. So this whole thing, arc sine of 0 is 0. So really, we only have this one. And if you want, you can divide here. You end up with, this will be 3/2 minus 1, which is really just 1/2. So we end up with the arc sine of 1/2, which again, you can leave as this on the AP exam, or you can work it out if you want to. You can say, okay, whose angle has a sine that's equal to 1/2? Well, this must be the square root of 3. All right, this is the short side, so this is pi over 6. So this must just be pi over 6. But again, this is an acceptable answer on the AP, and I believe this is also an acceptable answer on the AP exam. All right, so there it is. There's all of our integral rules. Really, there is one on here we didn't really go over, and that's this guy right here. All right, so it's a to the u just becomes a to the u with a 1 over ln of a out in front. All right, I think we might hit it later on, but again, it works the same as this basically. All right, but everything else on here we have done before, so you are expected to know all of these integral rules on this page. Really, if I'd say anything, this one and this one are probably the two that come up the most, the power rule and the natural log. All right, there will be some others later, like if you notice, like we don't have an integral of the natural log of x dx. That comes later. There's like a method for doing that. So there are some more integration methods coming. All right, so now let's compare and see if we can figure out which method would we use to take these integrals. All right, so we've got three integrals. They've all got the square root of x squared minus 1. This one has an x on the bottom, this one has an x on the top, and this one has no extra x's. All right, so which methods do you think we use for each one of these? Well, with this one, I can see if I just do regular old substitution, I get a 2 here and a 1/2 here, and we can do that one. This is substitution. All right, this one, let's see, if my u would then be x, my a would then be 1, du equals dx, and let's see, if I wanted to, I can put an x here and an x here, and this would be arcsecant, technically, of just x plus c. All right, so I keep leaving out my c's on arcsecants. This one, though, I don't know if we've covered this. All right, so we've got an x down here. We would need an x up here as well to do the arcsecant, right? And we don't have it. So I'm not sure what we would do on this one. Or either that or I've got them backwards. Hang on. Yeah, I switched them. Shucks. This one has the u on the bottom. All right, so this one would be the arcsecant. My bad. It's a long day. This is my ninth video I made today. This would be the arcsecant of x. This one, we wouldn't have anything yet. We don't have a way to do this yet. So the x over x thing doesn't work because we wouldn't have the x on top. All right, so this one we're still not sure of. There's going to be something that actually we don't do in this class anymore. When I took Calc BC, we did this. It's called trig substitution. All right, but we don't know that yet, so not in this class. All right, next ones, some more down here. So we've actually done this exact integral before. So x times ln of x, we said u was ln of x, and then du was 1 over x dx, and we had it right there. All right, so this one we could do with just substitution. This one we can also do with substitution. U is ln of x, du is 1 over x dx. Here's my du right there. All right, so this would be the integral of u du. So it'd be u squared over 2 plus c, or ln of x squared over 2 plus c. I know I didn't finish doing this one, but we've done it before. All right, this one, we don't have anything to use for our du. Like if there was an x on the bottom, it actually makes it easier. So a more complicated function actually becomes an easier integral here with the natural log of x. So we don't know this one yet. We will have a way to do this one, and this is called integration by parts. All right, but that's coming later. So we're not doing that yet. We'll do that one later. All right, so that is our integral techniques. So that's the end of integral rules and some more integral techniques. There is one more video, and it's the trapezoid rule.